In geometry, any two figures that have the same shape are described as similar. For this reason, we say that all circles are similar to each other. Representing the circumferences of the circles in figure 8.39 by C sub 1, C sub 2, and C sub 3, and their respective lengths of diameters by D sub 1, D sub 2, and D sub 3, we claim that C sub 1 divided by D sub 1 equals C sub 2 divided by D sub 2 equals C sub 3 divided by D sub 3 equals K, where K is the constant of proportionality. Postulate 22. The ratio of the circumference of a circle to the length of its diameter is a unique positive constant. Definition. Pi is the ratio between the circumference capital C and the diameter length d of any circle. Thus, pi equals capital C divided by d in any circle. In the following theorem, the lengths of the diameter and radius of the circle are represented by d and r respectively. Theorem 8.4.1. The circumference of a circle is given by the formula capital C equals pi d or capital C equals 2 pi r. In calculating the circumference of a circle, we generally leave the symbol pi in the answer in order to state an exact result. However, the value of pi is irrational and cannot be represented exactly by a common fraction or by a terminating decimal. When an approximation is needed for pi, we use a calculator. Approximations of pi that have been commonly used throughout history include pi approximately equal to 22 divided by 7, pi approximately equal to 3.14, and pi approximately equal to 3.1416. Although these approximation values have been used for centuries, your calculator provides greater accuracy. A typical calculator will show that pi is approximately equal to 3.141592654. Note, the number of decimal places shown may vary from calculator to calculator. In circle O in figure 8.41, length OA equals 7 centimeters. Using pi approximately equal to 22 divided by 7, A. Find the approximate circumference capital C of circle O. Solution. A. Circumference equals 2 pi r equals 2 times 22 divided by 7 times 7. Circumference equals 44 centimeters. In circle O in figure 8.41, length OA equals 7 centimeters. Using pi approximately equal to 22 divided by 7, B. Find the approximate length of the minor arc, arc AB. Solution. Because the degree measure of arc AB is 90 degrees, we have 90 divided by 360, or 1 over 4 of the circumference for the arc length. Then, length of arc AB equals 90 divided by 360 times 44 equals 1/4 times 44. Length of arc AB equals 11 centimeters. Informally, the length of an arc is the distance between the endpoints of the arc as though it were measured along a straight line. Two observations can be made with regard to the measurement of arc length. Number 1. The ratio of the degree measure m of the arc to 360, the degree measure of the entire circle, is the same as the ratio of the length L of the arc to the circumference. That is, m divided by 360 equals L divided by capital C. Number 2. Just as m, arc AB, denotes the degree measure of an arc, L, arc AB, denotes the length of the arc. Whereas the measure of arc AB is measured in degrees, the length of arc AB is measured in linear units such as inches, feet, or centimeters. Theorem 8.4.2. In a circle whose circumference is capital C, the length L of an arc whose degree measure is m is given by L equals m divided by 360 times capital C. Note for arc AB, length of arc AB equals the measure of arc AB divided by 360 times the circumference. Find the approximate length of major arc ABC in a circle of radius 7 inches if the measure of arc AC equals 45 degrees. See figure 8.43. Use pi approximately equal to 22 divided by 7. Solution. The measure of arc ABC equals 360 degrees minus 45 degrees, which equals 315 degrees. Theorem 8.4.2 tells us that the length of arc ABC equals the measure of arc ABC divided by 360 times the circumference, or length ABC equals 315 divided by 360 times 2 times 22 divided by 7 times 7, which can be simplified to length of arc ABC equals 38.5 inches. A limit represents a numerical measure. In some situations, we seek an upper limit, a lower limit, or both. Find the upper limit, largest possible number, for the length of a chord in a circle whose length of radius is 5 centimeters. Solution. By considering several chords in the circle in figure 8.44, we see that the greatest possible length of a chord is that of a diameter. Thus, the limit of the length of a chord is 10 centimeters. Note, in example 3, the lower limit is 0. That is, the smallest length of a chord is 0. Let a regular polygon of n sides be inscribed in the circle. As we allow n to grow larger, often written as n, arrow to the right, infinity, and read n approaches infinity, two observations can be made. Number 1. The length of an apothem of the regular polygon approaches the length of a radius of the circle as its limit. Apothem approaches the radius. 2. The perimeter of the regular polygon approaches the circumference of the circle as its limit. Perimeter approaches circumference. In figure 8.45, the area of an inscribed regular polygon with n sides approaches the area of the circle as its limit as n increases. Using observations 1 and 2, we make the following claim. Because the formula for the area of a regular polygon is area equals 1/2 the apothem times perimeter, the area of the circumscribed circle is given by the limit area equals 1/2 radius times circumference. Because circumference equals 2 pi r, this formula becomes area equals 1/2 r times 2 pi r, 2's canceled, or area equals pi r squared. Theorem 8.4.3. The area, capital A, of a circle whose radius has length r is given by capital A equals pi r squared. Find the approximate area of a circle whose radius has a length of 10 inches. Use pi approximately equal to 3.14. Solution. Area equals pi r squared becomes area equals 3.14 times 10 inches squared. Then area equals 3.14 times 100 inches squared. Area equals 314 inches squared.